My dear children, welcome to Riju and PSK online classes. This is laws of motion physics. Hope that you remember what was taken till the last class. Okay, in the last class, what we learned is that force is required. Of course, force is required to break and change the shape of things, but we are not discussing about that. We discussed that force is required to accelerate a body. Force is required to accelerate a body. That means force is not required if you don't want to accelerate a body. If a body is at rest, then you don't need any force for that. If a body is in uniform motion, you don't need any force for that one. If there is a force acting on a body, there will be an acceleration, provided the body is able to move. Okay. So, we have few questions from the NCERT textbook. Okay. These are those questions. Give the magnitude and direction of the net force acting on a body. Net force acting on a body. See, what is the purpose of net force acting on a body? You should know by this time that the net force F net, the total force acting on a body, is nothing but mass into acceleration of the body. The total force is mass into acceleration. And here we have to find out the magnitude and direction of the net force acting. And we know the magnitude can be calculated like using this equation, F net is equal to m into A. And the direction, what is the direction of the force? Direction of force is the direction of acceleration. So, direction of force is direction of the net force. Okay, direction of the net force is the direction of its acceleration. Okay, let us take the first example. A drop of rain falling down with a constant speed. A drop of rain. So, this is a rain drop. This is falling means downward with a constant speed. This is moving with a constant speed means it's moving in the same direction with the same speed. So, this is in uniform motion. So, this means the raindrop is in uniform motion. Raindrop is in uniform motion. Okay. If it is in uniform motion, what is the acceleration of the body? Acceleration is equal to 0. And now use this equation, F equal to mass into acceleration. That means the net force acting on the body, F net on the body is mass of the raindrop, let us say mass is m, into 0, that is equal to 0. So, this is having no acceleration, that means there is no net force acting on the body. Does it mean there is no force acting? Did I say no force acting or did I say no net force acting? There is a big difference between that one. In the case of a raindrop, there are actually two forces, at least two forces. One is the weight, the gravitational force, force of gravity, Fg, force of gravity. And there will be another force, at least another force. This is called force from air. Force from air. This force from air is of two types, you will learn later. One is known as the buoyant force. The second one is called viscous force. There are two forces acting from air in the upward direction and one force acting in the downward direction by gravity. These forces cancel each other. So, the net force will become 0. Okay. So, the answer to the question number A, net force is equal to 0. Now, it is easy. A cork of mass 10 gram floating on water. A cork is floating on water. Okay. If a cork is floating on water, then you can draw the diagram. This is the water surface and this is the cork. Okay. There is a cork here. This is floating means the cork will have the weight which is a gravitational force and the buoyant force from the water will be in the upward direction. Buoyant force will be in the upward direction and this is at rest. It is at rest. So, this is at rest. That means acceleration is equal to 0, which means the net force equal to 0. So, in the case 1 net force was 0, in the case 2 net force was 0. Fine. Third one, a kite skillfully held stationary in the sky. How to draw a kite? Say this is a kite, okay, this is a kite. The kite has got a string and you will hold the string. You will hold the string and there is a force acting on the kite due to the string, this one. Later we will study this as tension in the string. And there will be force from the air which will be acting in the opposite direction. Fine, this is the force from air. And this is skillfully held, means it is at the same location, it does not go up or down, it is at the same point. So we can say this is approximately at rest, it does not move too much. That means the net force, there is no acceleration, it is acceleration is equal to 0, that means the net force is also equal to 0. So third case also net force is equal to 0. Fine. So there is a downward force, there is an upward force, that cancel each other. Okay. Third one, a car moving with a constant velocity of 30 km per hour on a rough road. See, there is a rough road, this is a rough road, and there is a car. This is the car. This is going with a constant velocity of 30 km per hour. Constant velocity. That means this is in uniform motion. And if it is in uniform motion, what is acceleration? Acceleration equal to 0, exactly like this case. That means the net force is equal to 0. So in the fourth case also, net force equal to 0. Now fifth case is different. You can see that all the four, okay, I should tell you what are the forces acting on the car. On the car, the engine is providing a forward force and there is roughness. So frictional force will be acting in the backward direction, and this is actually not correct to say. Okay, later on you will understand that whatever I am telling is wrong. This is not correct. I will say there is frictional force acting. I will say there is the force due to engine and force due to friction. This will cancel each other. The directions are not exactly like this. And there are two other forces. Anyway, there are so many forces acting on the car, and that will make a net force equal to 0. That is balanced. Okay. So in all the four cases, there were forces acting, but there was no net force. But the last one, a high speed electron is a charged particle. Electron is a charged particle. Electron has mass. You know all this. Electron has got mass. But this is far from all material objects. It is far from all material objects means there is gravitational force which depends on mass, that is equal to 0. It is far means gravitational force is 0. And free of electric and magnetic fields. If electric and magnetic field is not there, then the electromagnetic force that we studied in the beginning is also equal to 0. That means there is no force. That means this tells you that there is no force acting. That means net force equal to 0. So how is the fourth case? How is the fourth case different from the first four cases? Fifth case different from the first four cases. In the first four cases, there were forces acting, but the total force was 0. In the last case, there was no force acting at all. But all the cases are similar. No acceleration. In all the 5 cases, acceleration is 0. Okay. Now from this we will go to the next question. Based on the same idea, a pebble of mass 0.05 kilogram is thrown vertically upward. You can try this at home. You can take your mobile phone. And throw upward, and you can check whether this is right. Or your laptop, anything, you can throw it. I know you feel like throwing this upward. I know you need to escape from these classes. A pebble of mass 0.05 kilogram is thrown vertically upward. Give the direction and the magnitude of the net force on the pebble. Okay. And there is one last sentence, neglect air resistance. So there will be only one force present, that is gravitational force. So the stone is thrown upward. So this is a stone which is going upward with a certain velocity at a particular instant. Is there any force acting on it? Definitely there is a force acting on it, that is in the downward direction. That is what we call as the weight of the body, which is a gravitational force. So magnitude of the net force on the pebble. Give the direction and magnitude of the net force on the pebble during its upward motion. Pebble is thrown, mass is given, and the acceleration is due to gravity, which is 9.8. So that should be equal to 0.05 kilogram into 9.8 meter per second square. That is the magnitude of the force, and the direction is downward. Fine. Second one, see, that is the during upward motion. Now say after some time the body will reach the highest point, then this will start falling downward. When it is falling downward, again the force acting is mg, same magnitude. Fine. Now at the highest point where it is momentarily at rest, so from the ground if you throw that one, at the highest point that will be at rest, its velocity will be equal to 0, but at that time also there is a force acting that is equal to mg. So you studied this in motion in straight line, motion in plane, and you throw anything in the air, there is gravitational force acting on it, and it's always downward. Fine. So during upward motion, during downward motion, at the highest point there is a force acting on the body. We neglect air resistance, that is equal to mg. Now do your answer change if the pebble was thrown at an angle of 45 degree with the horizontal? Assume that you throw this thing at 45 degree, then this will follow a parabolic path. Tell me, why does it follow parabolic path? Because there is a force acting. Why doesn't it go straight up like this into space? Because there is a force acting downward. At every point there is a force acting, and that is mg. At every point there is a force acting mg. Okay. There was a different force when you threw that one. Just before, like suppose you were throwing this using your hand, then just before it leaves your hand, as long as you have a contact on that one, there is your force acting. As long as the contact, but once this contact is lost, then my force will not act on that one. Okay. So then while it is in motion, there is only one force acting, that is gravitational force. And what is the direction of gravitational force? That's always downward, vertically downward. Fine. Now let us try this thing. Give the magnitude and direction of the net force acting on a stone of mass 0.1 kilogram. Okay, let us see. Where is it? See, that is about a train. There is a train. So there is a train. Say this is the compartment of the train. Okay. Just after it is dropped from the window of a stationary train. So this train is at rest. You are taking a stone. You are dropping it. So what will happen? The stone, suppose this is the window from you drop it, this is yourself, you are dropping it, and the stone will fall downward. So the force acting in the case 1, just after it is dropped, means only gravitational force will act on that one. So you can say that is F equal to mg, that is in the downward direction. Just after it is dropped from the window of a train running at a constant velocity. So the second case, the same train now moves with a constant velocity, you are dropping a stone from the window. Then for the person inside, for the person who is dropping it, it will appear to be falling in a vertical line downward. But for a person outside, this will fall forward along the direction and fall here. The path depends on the observer. For the person in the train, this is the path. For the person outside, this is the path. But anyway, there is only one force acting, and that force is again F is equal to mg. Air resistance is neglected because it is given, neglect air resistance throughout. Third case, just after it is dropped from the window of a train accelerating with 1 meter per second square. So in the third case, your train is moving but with an acceleration, its speed is increasing. In this case again, you drop the stone. For the person inside, this may fall in a vertical line, but for a person outside, this will follow a parabolic path. But there is only one force acting, that is mg, F equal to mg. There is no other force acting. But the last one is different. So I will say in all the three cases, there is only one force acting, that is gravity. Suppose I take my mobile phone, if I hold it like this, there is gravity pulling it down, I am holding it upward, there are two forces. But what will happen if I drop it to the ground? As long as it is in motion, there is only gravity acting on it, that is equal to mg. but when it hits the ground, there is a force from the ground. Okay. That's why I was so carefully holding my hand here, because if it falls on the ground, it can be dangerous. Last thing, lying on the floor of a train which is accelerating. So this is a train, okay. This is the train, see this is the floor, and the stone is lying on this train, and the train is accelerating at 1 meter per second square. Look at the stone. The stone is also accelerating. See, it's given the stone is being at rest relative to the train. That means for a person standing inside the train, the stone is at rest. That means the distance between the stone and the person will remain the same. It doesn't change. That means it is at rest. Just like I have a table. See, I have a board here. I am here, and you know, all of us are moving with the earth. But this is relatively at rest with respect to me, because that's also moving, I am also moving. So here, what is the acceleration of the stone? The stone is part of the train, and the train has an acceleration of 1 meter per second square. Therefore, there is a force acting, and this time I should say that the net force acting should be equal to m into a, where m is the mass of the stone, which is 0.1, into a is the acceleration of the train, that is equal to 1, that gives you 0.1 Newton force acting on it. Okay. Of course, there is weight acting downward and there are some other force acting outward, but the net force is equal to 0.1 Newton. That is the idea. Okay. So, that is it. Next one. Carefully read this. These can come in theory questions, come as theory questions. So all of them can be asked as a theory question. Like, see, in hitting or kicking a ball, we decrease the time of contact so that large force acts on the ball, producing a greater acceleration. What does it mean? If you want to play football, how do we apply a force on the football? You keep the football and will you slowly push it, or will you give a kick? You give a kick. And why? Because a kick means it takes less amount of time. A kick means it takes a less amount of time. We know that F is equal to what you call m into a. F is equal to m into a. Right. So, we know a is nothing but F divided by m. So, if you want a larger acceleration, you need a larger force. So, large force for producing greater acceleration, A is proportional to F. And how do we create that large force here? We know F is nothing but change in momentum by time taken. So, we can say F is inversely proportional to that time taken. So, if you reduce the time, force will increase. If you increase the force, acceleration will increase. The ball will get a large speed in a very short amount of time. So, the answer, hitting or kicking a ball, we decrease the time taken. Effectively, we are decreasing the time so that the force acting will be large, and force acting creates a larger acceleration. That is the meaning of this sentence. Okay. Second one, in catching a ball, a player by drawing his hand backwards increases the time of contact. See, suppose you are playing football, you want to take a catch in cricket. What do you do? How do we take the cricket catch? You have the ball coming and you hold it like this. You hold it permanent, fixed, like you keep yourself fixed, you hold it like this. And is it this way you can take a catch? Or will you move your hand forward, or will you move your hand backward? You move your hand backward along the motion of the ball. That means you are increasing delta T. You are increasing the time. So, the force will decrease. More time to catch, less force acting on your hand. Next time you can try pushing it in the opposite direction and the force will increase. You hold it like this one, fix your hand without moving, then hold the ball, there will be large force, but you move your hand backward, there will be less force. This is like a biological reflex. Suppose somebody is trying to hit you on your face. How will you move your head? You move it in the same direction like this, so that you can increase the time, decrease the force. Third one, in jumping on sand, the time of contact is increased. When you jump on, you can't easily walk on sand. That can be explained in very beautifully in using different methods. But this is one thing. When you jump on sand, the time of contact increases because of motion of the sand, and that decreases the force. That's why in sports, the jumping pit is filled with the sand. or something like that, similarly, which can actually move. That's why when you jump into water, you don't experience that much of force compared to when you jump on a hard surface, because the time of contact increases. Again, same thing, delta T increases, force decreases. An athlete is advised to come to stop slowly after finishing a race. After finishing a race, will you stop suddenly like this? You will not. You will run, keep running slowly, you will decrease your speed. This is to increase the time taken and decrease the force acting on the body of the athlete. Last one, Chinawayers or glasswares are wrapped in straw or paper before packing. While transporting, the glasswares are generally packed with like a thermocol, straw, paper, etc. Why? Because when they hit each other, the presence of the thermocol or the straw or the paper will effectively increase the time during which the force is applied. And when the time increases, the force will decrease, and that will reduce damage to this China wire. So these things can be asked in theory examination. Keep a very good interest in that one. Think practically, look around and find application of all these things. Now let us do this question. NCERT. Okay. Figure shows position time graph of a particle of mass 4 kg. The first data that you get from the question is that its mass is 4 kg. Mass is equal to 4 kg. And there is a position time graph given. Position time graph you studied, right? What is the slope of position time graph? Slope of position time graph. Slope of position time graph gives velocity. That is enough, velocity. What is asked? What is the force acting on the particle? What is the force acting on the particle for t less than 0? This is 0. Less than 0 means this part, t less than 0. Okay. Now we can see that this represents body at rest. It represents body at rest. When body is at rest, acceleration is 0, force acting on is 0. So we can say for t less than 0, body is at rest, so acceleration equal to 0, which implies that force acting is 0. That means it is not force, the total force, net force. Net force is written as sigma F equal to 0. Now t greater than 4. Where is t greater than 4? This is t greater than 4. Okay. So we can say for t greater than 4, body is again at rest because slope is 0. You can see this part slope 0, this part also slope 0. Slope 0 means velocity 0, velocity 0 means body is at rest. So acceleration equal to 0, that means the net force acting on the body equal to 0. Now 0, sorry, rather the t less than 4 greater than 0, that means t must be between 0 and 4, not 0, not 0, not 4, between 0 and 4 here. This is t less than 4 but greater than 0, in between. Okay. So we can say t is not 4 but less than 4, not 0 but greater than 0. What is the body doing? This represents uniform motion. There is a constant velocity. So the body is in uniform motion, which says that acceleration equal to 0, which says that sigma F equal to 0. Fine. So that is done. Now it's asked what is the impulse at t equal to 0? Impulse at t equal to 0. Okay, let us do that one. Impulse. We studied that impulse equal to change in momentum. Impulse equal to change in momentum. Okay, and that is given by final momentum minus initial momentum. Now see this. I told you this point is rest. This point is uniform motion. So initial velocity was 0. U was 0. So this is like a m into v minus u, which can be written as m into 0. Why 0? Initially, just before that it was at rest. But just after that, what was it doing? It was doing uniform motion. What is the velocity of uniform motion? Velocity is the slope. Okay. So we can say the slope of this thing, this slope is velocity, and we studied that x2 minus x1 by t2 minus t1 is the velocity. So that gives you 3 minus 0 divided by 4 minus 0, which will give you 3 by 4 meter per second. That is the velocity. So that I should write here, 3 by 4. And what is the mass of the body? Mass is 4 kilograms. So this is 4 into 3 by 4 gives you 3 Newton second. A positive impulse means the body speed increased. From 0, it started moving. So this is the impulse at t equal to 0. Impulse at t equal to 0 is equal to 3 Newton second. Okay. What is impulse at t equal to 4 second? Same thing, impulse is change in momentum, mv minus mu. But understand that when you are talking about this instant here, it was in motion and it came to rest. So the final velocity is equal to 0. Initial velocity is this thing. So this is like a mass is 4 kilogram, final velocity is 0, initial velocity is 3 by 4. Now this velocity is final for the 0 second, but initial for the 4th second. So this gives you minus 3 Newton second. This minus 3 says that it is opposite to the motion. Body was moving and it got stopped. That is why minus sign, opposite to motion. So we can say this is applied opposite to motion. It is applied opposite to motion. Is that okay? That is it. So please practice this. Oh my God, what is this? Figure shows the position time graph of a body of mass 0.04 kilogram. Suggest a suitable physical context for this motion. What is the time between two consecutive impulses received by the body? What is the magnitude of each impulse? If you look at this portion, you can see that this is just like the previous example. It might have been at rest initially, it started moving uniformly, and from the slope, xt graph slope 2 by 2, 1 meter per second is the speed. So you can easily calculate. But what happens here? Let me draw this like this, only the first part. It was at x equal to 0 and time equal to 0. From here it started, it took 2 seconds to reach 2 meters. This is a positive graph, positive slope, and the velocity is 1 meter per second. Now from there what happened? See here the velocity, the position was 0, 0, 1, 2. From there it started returning 2, 1, 0. It returned and it took 2 more seconds. So the motion of the body was that it was going to that side. After 2 seconds it returns. Then the graph says that it will go upward, downward, upward, down. So it is moving like this. This is the motion. Each time it is changing velocity here and here. In between there is no change in velocity. This is uniform motion in one direction, this is uniform motion in the opposite direction, this is a negative slope, this is a positive slope. This means one direction, that means opposite direction. It was changing velocity at 0 second, then at 2 second, then at 4 second. So the impulses received is in an interval of 2 seconds. And what is the impulse? Impulse is change in the momentum. Okay, change in momentum, that issue. Initially I don't know, here what was happening? At this point, what is the change in momentum? At 2 seconds, what is the change in momentum? At t equal to 2 seconds, impulse is delta p, which is equal to m into v minus u, which is, what is the mass of the body? It is 0.04 into, what is the final velocity here? What is the final velocity? You can see that the final velocity is minus 1 meter per second. Initial velocity is 1 meter per second. Why that minus sign? Because it was going forward and then reversing. So that reverse velocity is taken as minus. So we can say final is minus 1, initial is 1. So you will get this as 0.04 into minus 2. That gives you minus 0.08 Newton second. And the minus sign say this change is opposite to the motion. And at 4 seconds what will happen? At 4 seconds what will happen? At t equal to 4 seconds, the change in momentum, impulse is change in momentum, impulse equal to delta p equal to m into v minus u. And here at 4 second, initial is minus 1, final is plus 1. So this will give you like a 0.04 into 1 minus 1 will give you plus 0.08 Newton second. I can see these two impulses are in opposite direction. One is given in that point, another is given in this point. And so we calculated, suggest a suitable, that part I did not discuss, suggest a suitable example for this motion. Anyway, what is the time between the consecutive impulses? That is 2 seconds. And what is the magnitude of each impulse? That is 0.08. Okay. Okay. Now what is a suitable physical context for this one? A physical context means a practical example. What can you give as a practical example? Think about two walls, and there is a block. This block starts with the speed of 1 meter per second, and we assume that this is a smooth surface. So what will happen? The body will go and hit here. When it hits here, this wall will apply a force in this direction. That's for a very short duration of time. And due to that one, the body will stop and then it will reverse. So it was going in this direction, now it started moving in this direction. So this is taken plus 1 and this is taken minus 1 meter per second. So this will continue forward, backward, forward, backward. This is the position time graph of that body, and each impulses, one impulse is applied here from in this direction and one in this direction. So one of them is taken positive impulse, another is taken. So we got that 0.08 on one side and minus 0.08 on the other side, these two impulses. Okay. All right. So I think that was pretty cool. This one, a stream of water flowing horizontally with a speed of 15 meter per second gushes out of a tube of cross-sectional area 10 raised to minus 2 meter square and hits a wall nearby, vertical wall nearby. What is the force exerted on the wall by the impact of water, assuming it does not rebound? You must have seen this water cannon. Generally police force uses that whenever there is an agitation by the public to control them, they use this water cannon. Okay. And this water hitting on your body creates a large amount of force. You can fall down, you can even be carried by that one. Okay, water. Now you can try this at in your washroom, or open the water tap and keep your hand under that one. You can see that creates a large force on your hand. If you stand under a waterfall, the same thing happens. So falling water can create force on your body. But this is a very idealistic situation. Very idealistic situation. It says that there is a pipe. There is a pipe and there is a vertical wall, and water gushes out. Water gushes out like this. Without rebounding is not possible. Without rebounding is not possible. Definitely water will bounce. But if it is not rebounding, theoretically we assume that, then how much force is created by water on that surface? Okay. Now we can use the equation F is equal to delta P divided by delta T. Okay. The water was coming at a speed of 15 meter per second. But after hitting the wall, the velocity is becoming 0. So initial velocity is 15 meter per second, V equal to 0. Okay. Now this delta P by delta T can be calculated as mv minus u divided by T. mv minus u by T. Fine. Now we need to find out the mass of the water. That is not given here. Okay. So if you can calculate, and you can see that final velocity is 0. So this will give you minus mu divided by T, where mu is the initial momentum. Mu is the initial momentum. Fine. Now how do we calculate that one? For this, we need to study a bit more. Consider a pipe. Consider a pipe. Okay. In which some liquid is coming out. Okay. Now we can see, suppose the speed of that liquid is 1 centimeter per second, then in 1 second how much portion can come out? In 1 second, any section of water here will move forward by 1 centimeter. 1 centimeter in 1 second means this will move forward 1 centimeter. So we can say a cylindrical portion of water will come out. A cylindrical portion of water will come out. A cylindrical portion of water will come out. Okay. And a cylindrical portion of water will come out. In 1 second, 1 centimeter will come. In 1 second, how much will come? 1 centimeter will come, because speed is 1 centimeter per second. Suppose the speed was 2 centimeter per second, then the length of this will be equal to 2 centimeter. How did I get that one? I am saying in 1 second, how much will come out? In 1 second, 2 centimeter will come out. Fine. Okay. Now, let us make it little mathematical. Suppose the speed is v. Suppose speed of the water is v, and in a time t, how much water will come out? In time t, how much water will come out? This will be equal to v into t. Length of that one. In 1 second, 1 centimeter, that was our example. Now the speed is v, time is t, so the distance mode will be v into t. This much of water will come out. This is the amount of water, the flow, the volume of water which is flowing out. Okay. Now assume that it has got an area of cross section A. Area of cross section is A. Okay. Now what is the volume of this cylindrical portion? Its volume is equal to length into area. Area into length. This is the volume of that one. All right, like you see, so ordinarily we say pi r square into h. Here pi r square is A, and this is Vt. This is speed V, this is volume V. So be careful about that. Don't cancel that one. This is the volume of water coming out. What is the mass of water coming out? Mass is nothing but volume into density. So this will give you like AV into T into rho. This is the mass of water coming out. Fine. Now, what is the momentum of this thing? How much momentum is there? Momentum is nothing but mass into velocity. Mass into velocity, that is nothing but A into V into T into rho into V, which is equal to A V square rho into T. This is the momentum. Fine. But once it hits the wall, what about this? The initial momentum. Once it hits the wall, what is the momentum? That momentum will become 0. It stops, its momentum will become 0. Right. Now, how do we calculate force acting? Force is delta P by delta T, which is nothing but P final minus P initial by the time taken for that one. By the time taken. So this can be substituted. You can substitute P final equal to 0 minus P initial is nothing but A V square rho into T divided by T, and you can see that this T will cancel. You will get it as A V square into rho. This is the force with a negative sign. What is the meaning of that negative sign? Negative sign indicates that the force acting on the water from the wall is in this direction, opposite to the velocity. This is the force acting on this thing. Minus A V square into rho. Okay. So then now you can substitute that one and to calculate the force. So I think this part is okay. So you keep this in mind. Force exerted by fluid column by moving fluid column. F is given by A rho V square, where A is the area of the cross section, rho is the density, V is the speed. And here what is given? What is the area? 10 to the power minus 2 meter square. You should be careful whether it is all SI unit into density of water. You should know that is 10 to the power 3, not 1. 1 is in CGS unit. In SI system, that is 10 to the power 3000 into A rho V. V is nothing but 15 meter per second square. Okay. So this gives you 10 raised to 1. 15 square is 225. 225 into 10. 225 into 10. 225 into 10. This much of force will act on that wall. This much force will act on the wall. That is it. What is the force exerted on the wall by the impact of water? I hope this is okay. So, this session was all questions, and the previous sections were also like all questions. In the next session, we will have the third law of motion to be discussed. Till then, bye.